Hi, so welcome to this lecture where we continue our expedition with second order linear non-homogeneous ordinary differential equations with an exponential input. In other words, an exponential function of t. T is the variable, independent variable we are using on the right hand side. Now, just a recap of what we have learned in the previous lecture was that depending on how this small a this factor, going with t here, and this capital B and capital C, depending on how these factors play out, we have different forms of the particular solution. The particular solution of a differential equation was the solution which would satisfy this differential equation. So, depending on how these things played out, we had these different forms which we have studied. And we found these results extensively in the previous lecture. And let's build on these now, okay? So apparently it may seem a little haywire, all these results don't seem to be, we don't know if they are connected, if we can put them in one framework. Let's just try and do that. The answer is yes, we can put them in one framework and it's quite easy. So let's try to see how we can do that. So one thing to remember is that if you take the auxiliary equation of the homogeneous form of this equation, the homogeneous form would be just making the right hand side 0. The homogeneous form, once you make this into its homogeneous form and then take the auxiliary equation would be this, the quadratic equation. You all remember this from whatever we have learned so far. This has come up numerous times. So m squared plus bm plus c is equal to 0. That's the auxiliary equation for the homogeneous form of equation 1. Now, if I want to write this left-hand side, which is a function of m, the unknown variable here, it's a quadratic equation. It's a polynomial of degree 2. I want to write that as some function g of this variable m. Okay, then once I give this quadratic form, this polynomial of degree 2, once I give it that name gm, we can see that this denominator here is just ga, because if you put a instead of m, you just get a squared plus bm, ba plus c, and that's the denominator. So what we can do is, we can sort of write this equation not in terms of a, b, and c all the time. We can just write that this will be equal to ga if this is also ga, if this ga is not equal to 0. G of a, okay? That's a bad habit calling it ga. The function g of the variable a is not equal to 0. Well, what about this one? This is 2a plus b. Well, this is actually g differentiated once with respect to m, of course, that's the variable, and you put a. So g differentiated is 2m plus b. If you differentiate this once with respect to m, and instead of m, if you put a, you get 2a plus b. So this is really g prime a. And this is, well, this is ga, this whole thing. G of a, right. And this is g prime of a. Is not equal to 0. Okay, what about the last one? There's a 2. How would we get a 2 in terms of g? Is if you differentiate this twice, and then if you put a or whatever, if you put a, let's do that. So gm, g of m differentiated once was 2m plus b. If you differentiate g of m twice, that is, differentiate this once more, you would get just 2. It's a linear polynomial. There's only one variable, m. And then if you put a, well, nothing happens to it because it's a constant. So this is really the double differentiation of g at a. And again, writing this is if this is g of a equal to 0 and g prime of a, 2a plus b was g prime of a was also 0. Okay, so I think that's a much concise and a much better way to sort of bring all these different cases together. That is, when the moment you have an exponential input on the right hand side, you look for the auxiliary equation, which is really just replacing x double prime by m squared, x prime by 1m, and x by 1. Okay, c into 1 here. And then once you have that, you know what is the GM, it's just the left hand side, and then the particular solution will just follow this framework here. Okay, so that's really the summary. You can call it the summary of the particular solutions for second order linear non-homogeneous ordinary differential equations with exponential input. Okay, all right. What we do now is, once we have established what these particular solutions will be, depending on how things will play out, how this function is, whether it is how this function is behaving at a, whether it is 0, whether this is the velocity of the function at a. If it is not 0, this is, like that. If the velocity is also 0. So depending on how this function is behaving at a, you have these different forms. Once you have established this, we come to the last part of this puzzle here, which is to find the general solution. Okay, so this is the last thing that is needed to completely solve a differential equation. We have so far done 2 parts. One is to find the complementary solution, complementary function, the solution, which I called xh. So complementary function, if I can just recap again, complementary function was basically, you knew that for the homogeneous form of this differential equation, which was really making the right hand side 0, for the homogeneous form of this differential equation, the 2 solutions, so that was just x double prime plus bx plus bx prime plus cx is equal to 0. The 2 solutions possible for this were, well, they depended on various things. So in the case that m1 and m2 were not equal, okay, but real, which is really the case of overdamping, that is b square. This is the case that, please refer back to the video where we had done this. B square was greater than 4c. In this case, the 2 solutions for this homogeneous equation were e to the power m1t and e to the power m2t. Let me just call them xh2 for m2 and xh1 for m1. In the case that m1 and m2 were complex numbers, which is the case that b square was less than 4c, in that case, the 2 solutions for this homogeneous equation was sine omega t and, well, there was a decay term, e to the power minus rt, okay, and the other one was e to the power minus rt cosine omega t. Okay, where of course r, this is a shorthand that was used. R was basically minus b by 2. Again, these are things that have been covered. in the lectures where we have done all of this. This is the case of underdamping. Omega, I omega was this value, this discriminant value, b squared minus 4c by 2, like that. Okay. So these were the two homogeneous solutions of this homogeneous equation. This was the one. XH2 could be this one. Okay. Well, and in the third case, that M1 and M2 were equal, and they were both real numbers. This is the case of critical damping, where b squared was equal to 4c, which was the case of resonance. In that case, the two solutions for this homogeneous equation were m1t. You could write m1 or m2, doesn't matter, they're the same. The other one was t e to the power m1t. This is your second solution. This is your first solution, h1. Okay, so anyway, so the complementary function, the way I had defined was really a combination, a linear combination of these two functions, linear combination c1 with xh1 plus c2 with xh2, where c1 and c2 are constants. Okay? And you will, once you do this, you will get back all the results that we have covered in the previous videos. So this is a linear combination. Okay. Now, so why did we do this? This is the complementary function of this differential equation. Okay. This is one part that we have learnt, and this is really a recap, but it's important to write it down because we will need them. The other parts, this is one. The other thing that we have learned is to find the particular solution, or sometimes it's called particular integral, particular solution, which really was, that formula which we had written out. I'm just going to call it xp. Okay, remember these are all functions of t, time. Okay. Now, as I said, we are now looking at what would be a complete solution for this differential equation. Well, the complete solution for this differential equation will now be, and it's easy to see, and I will explain, it's going to be the complete solution. So let's just write down. This is the complete, this is the climax of what we have been doing. The complete solution of equation 1 is going to be xp, which is the particular solution given in terms of t, time, plus the complementary function, which really is, or let's just write that, the complementary function, which is again a function of time. So that's just xp t plus c1 xh1 t plus c2 xh2 t. This is what I call, this is that function x of t. The complete function, the complete solution which satisfies this equation. Why is it complete? Again, we invoke the rule of adding homogeneous solutions or weights of homogeneous solutions to particular solution. If this is a particular solution, it already satisfies this. So I'm adding a weight C1 of this homogeneous solution, one of the homogeneous solutions, xh1, depending on which one it is. In this case, you will have xh1 as an exponential function. In this case, you will have a wave, a decaying wave. Okay. In this case, you will have another exponential function, whatever. So depending on which one it is, if I add a weight of the first homogeneous solution, then this remains a particular solution, and we have proven this result, because if you put it here, it will satisfy. It will spit out this exponential. Now, if this whole thing is a particular solution, then adding another weight of another homogeneous solution still keeps it a particular solution, because we're following the result sort of like in a chain. Okay. So, and since we have no more solutions left, We're running out of this. We're running out of the number of solutions we can have. One possible was this. The others were this for the complement for the homogeneous function. So once we have written out all the possible things, this is what I'm calling it a complete solution, but really it has a name. It's called the general solution. The general solution. And that is really the climax, because when we say solve a differential equation, what we are looking for really is the general solution. So this is why is it called a general solution? Because we have kept the constant C1 and C2 open for interpretations or use or whatever. We have not given C1 and C2 any particular values. And that's why it is not a particular solution. Depending on who's using it, in which situation, and for which example, you can, impart different values to C1 and C2, and you will have then it will become a particular solution for that particular problem or example. But as long as you don't put numbers, particular numbers in C1 and C2 and leave it, like that for interpretations, then this is what would be known as a general solution. And therefore, this is, as I said, it's the climax of this expedition, where we have fully solved now, completely solved in the most general form, this second order linear non-homogeneous ordinary differential equation with an exponential input. Okay? We will continue with more examples in the next lectures. So much for today. Thank you.